Hi, so this is part two of my lecture on the trig substitutions. The three of them are standing here in front of us again. I just wanted to try to help you realize under what circumstances you use any particular one first. And it has to do with the algebraic expressions you see on the other side of the triangle, like the square root of a squared minus x squared. If you see something that looks like a constant squared minus the variable squared under a radical, that's a clue that you're going to be wanting to use the sign substitution. Similarly, if it's the sum of the squares of the variable and some constant, then that's going to be the tangent. If you see the difference but in the other order, that's the secant substitution. So I'm going to do another extended example, maybe not quite as long as the last one, but interesting nonetheless. And part of our job is going to be figuring out which of the substitutions we're going to use. So the integral I'd like us to try to do has the square root of x squared plus 2x minus 3. Double checking. Minus 3, yes, in the numerator of the integrand, and x plus 1 in the denominator. And that's an integral with respect to x. I had limits worked out too. Let's see, it was from 1 to 3. Okay. These are just chosen to make some numbers work out nicely. So, okay, you're presented with an integrand like that, and it looks pretty bad. It doesn't look like a variable squared plus or minus anything in there. There is a standard trick, however, that you should remember probably from high school called completing the square that will let you, modulo the fact that you'll change variables a little bit, let you re-express that as a sum or difference of squares. So just quickly, let me put this a different way. If we were squaring something and we got x squared plus 2x plus, well, just ignore what the third thing would be. If we were squaring something and it ended up with an x squared plus 2x, doesn't it necessarily have to be that we were squaring x plus 1? I mean, first times first will get us the x squared, the outer times outer, and the inner times inner terms will get you the 2x. The problem is it doesn't give you minus 3, it gives you x squared plus 2x plus 1. Right, but this is just 4 different from that. The constant is minus 3 as opposed to being plus 1. So you could say that x squared plus 2x minus 3 is actually x plus 1 squared plus or minus something. What would that plus or minus be? We'd have to subtract 4, right, to get that to look like. Okay, so this was sort of a bit of scrap work I just put up here. Let's return to the integral. Let's maybe call this integral I. I is equal to, well, this is just an algebraic manipulation. We've got x plus 1 squared minus 4 over x plus 1 dx. And I hope you're seeing that that was the kind of point of doing that was to set us up for a u substitution. This is where we want to let u be x plus 1, in which case that's just a linear substitution. The differential du is the same thing as dx. So nothing new there. So yeah, we got our integral in the form of a radical u squared minus 4 over u. Notice the limits are missing right now. It might be smart to put them in, and I think it's wise to figure out what they are in terms of a new variable u in this case. U is just x plus 1, right? So the original limits were x was 1 and 3. If u is x plus 1, that's not so hard. They're just 2 and 4. Okay? So lower limit is 2, upper limit is 4. Now, which of the substitutions that we've talked about is is appropriate in this scenario. We've got a radical of square root of the variable squared minus a square of some constant there. So, well, think about the triangle and you'll see that it's the secant substitution. The secant one is where the variable is on the hypotenuse. The constant, in this case it's a 2, is there. And what is this third side or side opposite? Well, it's the square root of hypotenuse squared minus that guy squared. Yeah, u squared minus 4. Great, so so the substitution we're using then is u is equal to 2 times the secant of theta. And I'm going to be a little smarter this time around and figure out what du is right now, because we're going to have to replace both the integrand and the differential on the end there. So if u is if u is twice secant theta, du is going to be 2 times secant tangent theta. D theta. All right, so the ratio of this radical over u, that's the side opposite the angle theta divided by the hypotenuse. Remember, theta is right in here. Didn't label it. But that's opposite side divided by hypotenuse. That ratio is actually just the sine of our angle. So we've got sine theta there. And then du is 2 secant tangent d theta. I'm going to leave the 2 out front and put secant theta, tangent theta, d theta after. That's a pretty hairy thing to figure out. What I usually like to do in these scenarios is just write everything in terms of sines and cosines first, and then sort it out in the end. So we've got 2 times the integral sine theta. Let's write that as sine theta over 1, because these are other things that are going to be fractions. Secant theta, that's 1 over cosine theta. And then tangent theta is sine theta over cosine theta. D theta. So all told, what are we looking at? There's a sine theta over cosine theta. Those two are a tan, and these two originally were a tan. We've got tangent squared. So I'll copy that onto the next board. Okay, so yeah, as promised, we've got the integral now re-expressed. Forget about that factor of 2. Tangent squared theta d theta. Now, you may notice the limits are missing again, because I know them in terms of u, but I haven't worked out what they are in terms of theta yet. So let's take a second and just do that. U and theta. U, the limits were 2 and 4. Now, I think it might help us to think geometrically about this. If u is the hypotenuse and the adjacent side is 2, what angle will correspond to what we get when u is in fact 2? That is, the hypotenuse will be the same length as the adjacent side, and that means it's really what's known as a degenerate triangle. The angle theta there would be 0. On the other hand, if u was 4, it doesn't look as I've drawn it here, but rather it's kind of a long, tall triangle if this length is twice what this one is. In fact, that's a standard triangle. Let me try to sketch it in here. If the hypotenuse is the double of the adjacent side, those numbers seem familiar. That's what you do when it's a 60-degree angle in there. Oh, I shouldn't talk about degrees. Pi over 3. Pi over 3 is the angle in there. All right, so that's what we've got. Pi over 3 at the upper limit, 0 at the lower limit. We can fill in these limits. And work away. Now, I feel like this was sort of scrap work, so I hope you're not upset with me for just getting it out of here. can we integrate the square of tangent? That's actually something we did in section 8.3, where we were looking at various trig functions with powers on them. But this one actually yields to a particularly nice little trick. You've got, you can use a Pythagorean identity. Maybe I need some more scrap paper here, because I feel like sometimes people aren't as facile with the Pythagorean identities involving tangents and secants. So let me just briefly show you how to convert the usual guy, sine squared plus cos squared equals 1, into an identity involving tangent. You just sort of want to make it happen, right? Look at this first fraction, or sorry, first term, and create a fraction that looks like tan squared. Well, that means you have to divide it by cosine squared. Of course, that's not legal unless you do it to all the other parts of this expression. Right, so after dividing through by cosine squared, we've sort of manipulated the original Pythagorean identity into one that says that tangent squared plus 1 is equal to secant squared. Or if you, since we want to know what tangent squared is, let's just subtract 1 from both sides and get that version of it. All right, so tan squared can be replaced with sec squared theta minus 1. You can think about that as scrap paper, but let's put the result in right here. Secant squared, whoops, needs a C. Secant squared theta minus 1. Why is this a nice trick? Well, secant squared is the derivative of tangent, so when we're anti-differentiating, we'll just get tangent there, and we can certainly anti-differentiate 1, so our integral can actually be computed now. We have 2 times tangent of theta minus theta, all evaluated between 0 and pi over 3. And you should notice that at the lower limit, both of these terms are 0. And at the upper limit, what we have is tangent of pi over 3 is root 3. So let's see. Yeah, it's 2 times root 3 minus pi over 3. So let's go look at what that is on a calculator. So this is a workstation setup. I can also do screencasting. There are 2 different modes of delivering online lecture stuff that I'm trying out. So this is one of them. Let's see. First, I thought it would be smart, as I want to do, to sort of get an estimate of our result before we actually do the work. I realize I've done all the work now and I'm just getting to the end, but this is the a Desmos graph of the function we started with originally, square root of x squared plus 2x minus 3 over x plus 1. And you can see it's a funky looking thing. Notice there's a nice big region in here where it's undefined between minus 3 and 1, and that corresponds to where this quadratic x squared plus 2x minus 3 there is negative. So what's under the radical? When what's under the radical is negative, the thing goes undefined. Fortunately, our limits were between 1 and 3, so we're missing out the portion where it's undefined. So actually, let me limit the domain to that range. So 1 less than or equal to x less than or equal to 3. That's the portion that we're looking for. It's really the area under this graph. I'm actually really getting fond of this trick in Desmos where you can specify a region by giving an upper and a lower bound for the y variable as well as for the x variable. So that's what we're after right there, is the area of this region. That's what that integral will be telling us. And we can get a pretty close guesstimate on that. The region is about 2 units wide. That's right, it's exactly 2 units wide. How tall is it? That's, did you see that? 0.866 is the height of the thing. So if it was a rectangular thing, it would be 2 times 0.866, or around 1.6. It's not a rectangular thing. If it were a triangular thing, then it would be half of that. And I think what reality is, it's somewhere in between being a rectangle and a triangle, right? So I'm going to use the average of those two numbers, and let's get that on the calculator. So 2 times 0.866, and well, the average of that with the half of itself, in other words, I want 3/4 of this guy, 0.75 times. Okay, so we should get an answer around 1.3. Now, what was the answer we actually got? It was 2 times the square root of 3. Square root. Am I hitting the right button? There it is. 2 times the square root of 3 minus pi over 3. Alright. That looks right, and that is, well, it's a little bit bigger, but not a whole lot bigger, around 1.37, so I think that agrees pretty nicely with our estimate, and I'm willing to accept it as correct. Yay.